Okay, so thank you very much for giving me the opportunity to present some of our work at this interesting conference. And it's a great pleasure to be in Riga, or at least on this conference. I would very much like to be in place, but so these are the options. And it's great to have this introduction to all the magnificent activities that you perform. And my relation to the University of Latvia is very recent and started in this winter when we discussed. I was contacted by Ulrich Berchint to see if we can have some common collaborations on lifetime measurements and also on spectroscopic measurements for astrophysical applications. So I will review some of the work we do and some of the plans we have for the future in our group of atomic astrophysics. And this is a large collaboration between many small units. This is really standing on the shoulders of giants. So the atomic astrophysics has its origin at Lund University in our group in the times of Bengt Edlén, and then later by the late Sven-Erik Johansson, and in a great collaboration within the Lund Laser Center with Sune Svanberg as the head of the center, but also with a large group around Lars Engström and Hans Lundberg, and also with all the collaborations with atomic physics, but also within combustion physics. And then in the latest 10 years, I've moved my activities to Malmö University, which is a close-by university, but we still have the great collaborations and interactions with Lund University. So some of the ideas I will discuss today will be in collaborations with Lund University. So here are some of my colleagues, and so in Malmö, Lund, and international as well. And looking forward also to see what can come out from the collaboration with the University of Latvia. So I will start right off with the conclusions. And so our aim of this program and the work within atomic astrophysics is really to provide a set of accurate and evaluated data for transition data for astrophysics. And so we do an approach where we do laboratory measurements and calculations, and these combined can then provide a great set of data for astrophysical analysis. And an important part of this are the given uncertainties, so we can give a realistic uncertainties, but also give uncertainties for all the data. And I will say that our new focus is the near infrared region, so 0.8 to 5 microns. This is new region for our studies. I will come back to that as well. So we'll start with some astrophysical motivation and also discuss near infrared transitions. I will describe the experimental technique, which is the high resolution spectroscopy and the lifetime measurements, and also provide an outlook afterwards. So if you go back and have a general view of the principle of abundance analysis of stellar objects, it can be stars, it can also be other exoplanets, there can also be galaxies in general. So I tried to do a sketch, and then in the upper left, you have the observations. Here's the spectrum of the sun. And you provide, to get the chemical analysis for the stars and the interstellar medium, you need either you can compare with a theoretical spectrum, or you compare with you measure the spectrum directly. But one important thing for this analysis is the atomic data. So the parameters we will provide in the studies, what we study are the atomic data and the atomic processes, that is the excitation and de-excitation and ionization and such, for the atoms. That's what we provide. And together with the galactic evolution models, then I mean the main goal of these activities is when and where were the elements formed, basically all the elements that build up our body. So if you go back to the periodic table, there is this notion that some of these elements are produced at different sites. So the basic elements, I mean, they are produced in the Big Bang, and the result for the Big Bang nucleus synthesis. And elements then up to iron are produced in the stellar cores and then spread in the supernova explosions. But if you see that all these purple elements here, they are produced in merging neutron stars. That is the current thought. So in the great neutron flux, which is in its mergers, will then produce these elements. And also in the low mass stars, you can see the green elements. So our goal is then to study different kind of elements that can probe the different nuclear synthesis in these different objects, and then work back, I mean, to provide important clues to what's the abundance in different objects, and then from the abundance, the galactic evolution people can derive what are at the origin of the different objects. And why infrared? Well, this is a picture of the Hubble Space Telescope of the Eagle Nebula, or the creation of the pillar of creations. And you can see a few stars in the blue region, but in the central dark region, there's not much light. And that's because these are molecular cloud and dust clouds, and these are not transparent to optical light. But if you look in the infrared region, you can clearly see that there's a lot more stars, and these pillars, they get transparent. So it's the infrared light can then go through this gas, and you can see much more. So this is of course important then if you want to study places with high extinction. For example, the galactic center and stars and stellar clusters close to the galactic center. And so then you might wonder, I mean, this sounds, looking at the atoms, deriving wavelengths and transition rates, this sounds like a 20th century, early 20th century science. So after 100 years, are there still stuff to do? Is it still interesting? And as was pointed out in this Nature editorial text, that the laboratory-based experiments, they are accurate, urgently needed to get this good analysis. So still after 100 years, when we put observatories for billions of euros into space and on ground, this is really still, the analysis is hindered by this atomic data. So for just a few extra euros, these activities are not the really costly ones. So then you can really get all the benefit what you want from your observations. This was clear when the Hubble Space Telescope came along on sky in the 90s for the UV and the optical as well. And now when we started to explore, but astronomers started to explore the infrared region, this is even more clear because that's not been interesting in this region before. So for the infrared, you have several orders of magnitude less extinction. The atmospheric transmission bands are a problem, but there are some bands around 1 micron, 1.2 microns. And for cool stars, this is important. And you might, if you explore an atomic database, you might think that the only molecules in the near infrared region, and this is because no one did any work on the atomic data. So there is prominent lines in the near infrared between 1 and 5 microns, but in the database that's very scarce. So that's why we study the infrared as one of these. And what atomic transition would you expect in the infrared? So from an atomic physics point of view, where I have my training, what kind of lines would you see? Well, the natural guess would be that you could see this high excitation transition, like the Riga transitions. And they are, of course, prominent in stellar spectra. But there are other transitions as well. So the lower excitation transition in some of these complex atomic spectra are also prominent, and also the resonance lines for heavy elements, like the rare earth elements, they will also fall in the 1 to 5 micron region. So these are the ones. So if you look in the periodic table, the elements we want to study, these are the iron group elements. where we would see high excitation lines. And I will give an example. If you look at the energy level spectrum of iron 1, this is a simplified energy level diagram. I mean, you might be familiar with it, but for the example, the most prominent iron 1 lines that appear in stellar spectra are the ones between the 5s and 5p. And of course, these are quite high excitation lines. But if you look at due to the structure of the atom, the promotion energy between the 4s and the 4p here, that's very strong, and these will fall in the optical. So there are no low excitation infrared lines in iron, not in iron 1 and not in iron 2, for example. But if you go to these higher elements, this is about the same. So the p elements for these light elements, which are very important for astronomical observations, they have the same case. So we have studied these with both calculations and experiments to get these complete sets of data. If you go to another group of elements down here, the strontium, yttrium, and lanthanum, they have a structure which make them appear infrared lines. So in principle, you have the same energy. There's a very small energy difference between the 3D and the 4S energy configurations here. So the 3D 4S squared, the 3D 3, and the 3D 4S have similar energies. So for these elements, they differ in quantum. They are homologous, so they have the same atomic structure, but quantum numbers. So for scanning 1, you have 3D 4S squared and 3D 2 4S. And for yttrium, you have 4D and 5S, and for lanthanum, you have 5D 6S. And all of these elements are very important for chemical analysis in stellar spectroscopy. And then you can get these in combination lines. You can see this. So these lines will fall in the one micron region, and they have a very small excitation energy. So it's about 1 electron volt, so 10,000 inverse centimeters. And if you apply if you have a cool star and you have applied the Boltzmann factor, you can really see that these lines will show up strong compared to the Rydberg states, which have much higher excitation energy. So these lines will then be very important probes for chemical abundances. Okay, so what's then what's the technique? So I will just review. I know that many of you are active in this region, or this field as well. But so the F value or the Einstein A coefficient can be derived from basically from two separate measurements, from the branch infraction, which is for a given upper level, how much of the emission comes in each channel for this particular upper level, and then combined with a radiative lifetime. So, and combining these two can then give the A value, the transition rate or the transition probability, which is then the absolute factor. And if you take this example, you can see that in this case, you have an infrared transition. For some of this level, there is an infrared transition, and there's also an optical transition to the ground state. And of course, but for the other states, there's only an infrared transition. And from astronomy, this point of view, that would be equal lines to study. But if you look from an atomic physics point of view, one of these would be easier to measure for one reason and than the other. So if you look at different states which have optical lines, like the lower states here, and one that don't have it, it's a bit tricky to different challenges to measure these values. So if we have a decay region, a certain level, either you can have only optical lines, or you can have optical and near infrared lines, and you can have only near infrared lines. And given from the scaling of the A value, that will scale with a wavelength. So if you have only optical lines, you have a narrow spread in your lines. So all of the lines show up in the optical region. It's easy to measure the branching fractions because all of them show up in the same wavelength region. So the calibration and coverage with detectors will be much easier. And the lifetime will be somewhere in the range 1 to 20 nanoseconds, which is fairly easy to cover. If you have optical and infrared lines, you will be a large branching fraction spread that would spread around a large region, so that will be quite hard to calibrate. Whereas the lifetime, which is set by the strong lines, will be easy to measure. Whereas if you have only near infrared lines, your branching fraction will be easy to measure, but the lifetime will be more challenging with 1 to 10 microseconds lifetime. So you can see that if you want to do near infrared lines, either the branching fractions or the lifetime will be a challenge compared to the optical lines. So this is one of the challenges when we move to the infrared wavelength region for this spectrum. Our workhorse for this is for the spectroscopic measurements. I will now give some highlights from the previous work where we measure the branching fraction of the lines, and also with the lifetime measurement afterwards. So the Lane laboratory, presently at Lund Observatory, it's a spectrometer which covers the optical region and all the infrared out to 5 microns. And it has a spectral resolving power of 10 to the 6, which is really needed to measure this complex spectrum. So this is a typical spectrum of a hollow cathode discharge that we use. So you can see there's a lot of lines, and the lines are very narrow. So if I zoom in, you can see that the Doppler width is 1,000. Measure the position and then the intensity of each line. So these are fully resolved lines. Because this is a single line, but sometimes you also experience the case of hyperfine structure. And this is also a very important factor when determining the F values. When modeling a stellar spectrum, if you don't include the hyperfine structure, the abundances can be off by an order of magnitude. And if you want to do chemical abundances to 5% accuracy, which is really what's needed to do separate populations of stars, this is gonna ruin your whole study if you're not careful enough. Previously, we measured the lifetime measurements at the VUV laboratory at the Lund High Power Laser Facility, within the Laser Center as well. This been a workhorse for several decades, and also producing very nice lifetime results. And I will not go into detail, but basically it's a laser-produced plasma, YAG laser, and which then is monitored through a photomultiplier. And one of the unique things of this laboratory, which was closed down 2 years ago, was then that we could measure states of very high excitation. So we have 2 different probe lasers. One for the first step, and then we did another step with a timed second laser. So the first step was covered with 1 laser, and then the fluorescence. So the basic idea, you have a laser-induced fluorescence. You apply a laser pulse to an upper state, and then in real time you observe the decay. Like in this case, so the dotted line is the fluorescence, the laser, and then you can see that the broader peak is then the fluorescence, and you can do a fit. And with this, you can measure lifetimes with an accuracy up down to 5%. So if we apply another laser, you can reach 1 step higher, and then you can measure the state lifetimes of highly excited state, which are very important for some of these hotter stars. And this has not been reported by any other laboratory. There are a few other laboratories measuring these laser lifetimes, but not for this second step. And then we have to time the 2 different laser pulses so that you pump when you have a high population in the first state. So this is an example of this. And here you can also reach a similar accuracy of 5% for these lifetimes. And so far, these highly excited states we've been measured. So the last performed measurements were done 2 years ago, and we covered basically all of the iron group elements, and also the next set, yttrium, zirconium, niobium. They have measured lifetimes for this 2-step or 2-photon excitations. It was a very good achievement. If we look back in the for these elements of scandium, we have these lighter elements. We combine experiments and also large-scale calculations, which are performed by Professor Per Jönsson in Malmö University. So we have a close collaboration. So we do the measurements for some levels, and then we do the calculations for the levels we cannot measure. And by this, we get a complete set of data. And you see, these are the measurement of in infrared for scandium, and you have the high values here. These are the strong lines, and these are the weak lines down here. So this approximates a transition rate to 10 to the 5, and here 10 to the 8. This is now in the log GF for those familiar with this. You can see for the strong lines, these are comparisons to previous calculations, and for the strong lines, the calculations do pretty well. For the semi-weak lines, it start to scatter, and for the weak lines, this is really not a good agreement at all. So before these measurements were done 5 years ago, this was the level, the values that astronomers were stuck with to measure the scandium abundance of these stars. So you can really see there is a need for high accurate values. So for one approach for this magnesium, silicon, and aluminum, we have the experimental data, the theoretical data, and also the stellar spectra to benchmark with. And these are the results we got a few years ago for magnesium. And you can see that, so the pluses are the calculations from us and all the experiments of the circles. And you can see that they agree pretty well for most lines. The crosses are the cruise values, so they differ by, these were the previous calculations available. There were no measurements available before. So you can see, and now this is a log scale, so really there is a difference between up to 50% for each of these lines. And magnesium is one of the key elements which is studied in the stellar spectroscopy, in the galactic evolution. So really, the uncertainties come from both the branching fractions and the lifetimes, and these are independent. So to get good A values down to a few percent, we really have to do accurate branching fraction measurements and accurate lifetime measurements. So before, I will just say something also about, are there no forbidden transitions in the infrared? Well, there are, and these can also be measured with the same technique, with the lifetime measurements and the branching fractions. But now the time scale and the transition rate scale is 9 orders of magnitude difference. So the lifetimes would be the transition rate would be 1 per second rather than 10 to the 8 for a E1 electric dipole transition. So clearly you need a completely different experimental technique. And then we have some work. So then we really need to have a low density plasma, very sensitive to collisions. So one very low density plasma is this star Eta Carina, which can provide us with excellent spectra. So if we have some HST spectra, we can get the branching fractions, and by using storage rings with can also A values for different transitions. Dag Hanstop later this afternoon will discuss more about, but please have a look at the site if you're interested. This is open for applications. We have projects. So for the outlook, we plan to, together with the combustion physics Lund, a new setup for lifetime measurements, and we can also get these near infrared transitions that we need. And for the spectroscopy, as I mentioned, there's been at the University of Latvia, there's a very successful development of light sources, and see if we can get a collaboration going that we can measure more of these highly excited states or more elements that we cannot produce in our light source. So this is something I really look forward to. And I mentioned the near infrared, but also the UV and the optical still have a lot of lack of data, where large improvements needed. So I'll end up here with summarizing. So we really need to focus on the near infrared data. This is a crucial demand from the new observatories. And if we have lab measurements of lifetimes and spectroscopy, we can really push down to this 5% accuracy. When we, especially if we combine it with calculations, we can get really complete sets of data, which is needed for these observatories. So thank you.
Hello, Dr. Ugelis.
Thank you very much for your report. It's really great coverage with our interests and our future interests. In case we are having more potential now for academic freedom, especially all this, being a team member of Verichair. Therefore, I see a good perspective for cooperation for long time ahead. Okay, I promised if colleagues agree to use some part of our lunch break for questions. The first question to Sune, first questions. Are there any want to ask to Sune something? At least I have one question to start. I thought that in case you are dealing with laser resonance fluorescence of mercury in an environment, it means you need to very sensitive detection system. You are coming down to photon counting or not?
Well, we are not running photo counting. You know, the signals are always pretty big, but of course the question is how big is the fraction in absorption?
Exactly.
You know, basically we are doing what everybody doing optical measurements using absorption, using the Beer-Lambertian law. And the size of your signal is the product of concentration and path length. So what about mercury? These concentrations of mercury are exceedingly low. We are talking about parts per trillion. You know, that's 1 part in 10 to the 12, which is typically 10,000 times less than sulfur dioxide or things like that. And the reason why we can see mercury is that mercury is the only pollutant in the atmosphere, which is an atom. We heard about atoms. Atoms don't fool around with a lot of rotational vibrational lines and so on, but have the oscillator strength in that. That is what we are using. So that is why we are 1,000 times more sensitive for mercury than for anything else, more or less. That's a lucky coincidence. That's the answer. And that means that we get reasonable signals out to 1 kilometer range, even if the concentrations are of the orders of few parts per trillion.
Okay, great. Thank you. More questions to Sune? Any questions to Lorenzo? I have only very short remarks that evidently there is some overlap with Professor Andres Ambainis. I don't remember, but seems you met him in Riga, Lorenzo, when you had been in Riga. He's also dealing with cryptology and quantum computing, and also Kashcheos is trying to do something on hardware of this quantum computing. I see prospects for future collaborations there. Okay, the last question to colleague from Malmö, to Henrik. Any questions? Uldis, you have question? Switch microphone, Uldis.
Yes, thank you, Henrik, for a nice report. And I hope you mentioned an facility in Stockholm, Desiree, has very good conditions for such an experiment. But there we have to study ions, since it's ion trap or ion ring. Probably you have some ideas what from ions could be studied there.
Yes, so the experiment is very successful at Desiree, but not for lifetime measurements of ions, but for negative ions, as Dag Haston will report, I guess. So this is not our workhorse, but for the we can start up to 50 lifetimes, up to 50 seconds. And A values for these forbidden lines.
I just realized that recently there were announcement for calls for projects to Desiree, and maybe we can think about to apply.
So this is also excellent temperature. So the temperature really molecules will reside in the very lowest states. But it's also connected to lasers. So an OPO with a large coverage, but also coming along next year.
Okay, thank you.
Okay, no more questions. Okay, thank you very much once more to all three presenters.